Okay guys, let's go ahead and go over this warm-up. It says, if the table shows velocity data for a car, what is its acceleration? And this is a table that has the velocities of, it says a car, for each second for 3 seconds. And so it says that initially the velocity is 0, and then after 1 second it's 1.5, and then 3, and then 4.5. What would be the acceleration of this car? What do you think? Yeah.
1.5?
Yeah, 1.5 with units, meters per second, or meters per second squared. But it's getting faster, 1.5 meters per second every second. That's where that unit comes from, meters per second per second. But yes, that would be your acceleration. So again, please make sure you have answered that in your warm-up in Schoology. And as I said, we're going to get into some notes today. So we've already talked about acceleration, and we've looked at examples like this where you're analyzing data and trying to figure it out. We haven't done a whole lot of calculations yet, and so that's what we're going to do today, is bring in some math to this discussion of acceleration. Okay, but before we get to that, let's see how well we understand that acceleration. Can an object have 0 speed and still be accelerating? What do we think? Could you have something that is not moving and still be accelerating? No. No, an object cannot accelerate if it's not moving. Okay, now I suppose you could have something that has 0 speed for just a moment. And sure, you could have acceleration at that moment, but no, you can't have something that's just sitting there at rest, and that object would not be accelerating. What about this one? Can an object have constant speed and still be accelerating? I see some no's and I see a yes. Okay, the answer to this is yes. As a reminder, if you need to write it down again, write it down again. As a reminder, acceleration is speeding up, slowing down, or changing direction. Speed is scalar. It doesn't care about direction. So if I just said 5 miles per hour, you don't know which direction I'm going. It is entirely possible for me to, ride my bike at 8 miles per hour and take a curve and turn at a constant speed, and yet that would still be an example of acceleration because my direction has changed. And as my direction changes, more and more of it becomes, let's say I'm going south and I turn east, more and more of it becomes east, okay, or eastward. And so since that's part of the value for velocity would be not just the magnitude but also the direction, whenever I have a change in my velocity or the direction of my velocity, then I'm going to have an example of acceleration. But yes, changing direction would be an example of acceleration even if you do it at a constant speed. All right, so let's see if we can analyze some graphs before we get to the math, just to refresh from last week. This is a position time graph, and it's showing the motion of 2 different people, Ava and Rip, and I think we actually looked at this graph a little bit previously in the last unit, so we're coming back to it. But it says differentiate between Ava and Rip's motion. So how are their motions different? Looking at this, what are they doing? Take a look. I'll give you a moment. You can talk to your neighbor if you're not sure. Okay, but I've got 2 questions up here. Differentiate between their motions, so tell me how they're different, and describe what's happening at 4 seconds. So I'm going to give you 23 seconds to turn and talk to your neighbor. I'm going to call on somebody, so you better have an answer ready just in case it's you. All right, that was 23 seconds. So let's see. Brant, what do you think is the difference between their motion?
Rip is going at a constant speed and Eva's accelerating.
Perfect. Rip is going at a constant speed, Eva's accelerating. I know that because Rip has a straight line slope and Eva's is a curve. Okay, so we know that that is true about their motion. What happens at 4 seconds, Kate?
Their position is the same, but Ava's passing him.
There you go. Ava's passing him. She was behind him. They're at the same spot, so she's passing him in that moment. Perfect. So again, be able to interpret those types of things. Rip's at a constant speed. Eva is speeding up. And at 4 seconds, Eva passes Rip. They're in the same location at that time. All right, what about these two questions? Again, turn and talk to your neighbor if you're not sure. But which person is traveling the fastest at 4 seconds and why? Which person travels the greatest distance in the first 4 seconds and why? So again, turn and talk to your neighbor. I'm going to give you 25 seconds this time, and I'm going to call on somebody. So be ready. If you're not sure, ask them what they think. All right, so who is traveling the fastest at 4 seconds? What do you think the answer is to that, Kieran? Kieran, you okay back there? Who's traveling the fastest at 4 seconds?
The fastest at 4 seconds.
Mm-hmm.
Aren't they going the same?
They are not.
I guess Eva then?
Eva is, yeah. So they're not the same speed at that point because they're at the same place. This is a position time graph. We answered that a second ago. But your speed on a position time graph is your slope. So although this is a curve, you can find the slope at that point, kind of by the tangent line at that point. But you can look at just the relative steepness of her graph at that point. It's definitely steeper than his. Second question, which person travels the greatest distance in the first 4 seconds? Ava, what do you think?
What?
Who travels the greatest distance in the first 4 seconds?
Eva?
In the first 4 seconds, how far has Eva traveled?
Can I change my answer?
Yes, you can.
Can I change it to Rip?
How far has he traveled? In the first 4 seconds, how far have they both traveled? That's what the question says.
Like three-ish?
Okay, both of them? Okay, so if they've both traveled 3-ish meters, then whose is greater? You want to help her out, Victoria?
Same.
They're the same. They travel the same distance. They're at the same point at that time. Okay, this is why I tell y'all to turn and talk to somebody so you have an answer ready. Okay, they travel the same distance in the first 4 seconds. Okay, all right. At what point in time do they have the same speed? I mentioned this a second ago. Speed is slope. So we're looking at what point in time are their slopes the same. And yes, Ava's slope is changing. Okay, it's kind of difficult to tell, but look for the point where they look roughly the same, where those two lines look roughly parallel. Okay, and you're going to find that point about right there. Okay, they're roughly parallel about right there, which means that at about 2.5 seconds-ish, okay, their slopes are about the same, and thus they would have the same speed at that time. All right, which person has the greatest average velocity for the first 4 seconds? Again, guys, average velocity is total distance divided by total time, and we're just looking at the first 4 seconds, and we've already answered this question twice, but they have traveled the same distance after 4 seconds. And thus, if it took them both 4 seconds to travel about 3 meters each, they would have the exact same average velocity because they have traveled the same distance and the same amount of time. Okay, so they would have equal average velocities at that point. All right, here is a velocity time graph, different type of graph. Okay, same question, different people, but differentiate between Art and Polly's motion. I'm going to set another timer, this time only for 18 seconds, but you better turn and talk to somebody so that if I call on you, you know what to say. Go ahead. All right. Bram, can you tell me how their motions are different?
Art is accelerating and Polly is staying the same speed.
Cool. Art is accelerating, Polly's staying the same speed. Perfect. Polly's moving at a constant velocity, specifically a constant velocity of 1 meter per second. Art, on the other hand, is speeding up from 0 meters per second to about 2.5 meters per second over the course of 5 seconds. Okay, you don't have to give me that much. This is fine. Polly's moving at a constant speed. Art is speeding up. Perfect. Okay, what is the significance of the slope on a VT graph? Okay, what does the slope mean? Polly has a slope of 0. Art has some positive non-zero slope. What does that tell me when I look at this graph and I figure out the slope? What do y'all think? Do you remember? Acceleration. This was in our notes last week. Okay, so the significance of the slope is acceleration. If you have a VT graph and you find slope, that is acceleration. Polly has 0 acceleration, 0 slope. Whereas Art has some acceleration here. It looks like his acceleration is 1/2 meter per second every second. Okay, so again, slope is acceleration. At clock reading t equals 3 seconds, who is traveling the fastest and why? I'm going to give you a moment to turn and talk to your neighbor and ask them. If you're not sure, have an answer ready. I'm going to call on somebody in 17 seconds. Okay, Issa, who's traveling the fastest at 3 seconds? You thought right. Art is traveling fastest at 3 seconds because he's traveling about 1.5 meters per second, whereas Polly is only traveling 1 meter per second. All you have to do is look at the y-axis at that point in time, which sounds like it's what you did. Okay, so again, you can look at those 2 points. Art, we just said that. What happens at 2 seconds? Again, turn and ask your neighbor. You have 21 seconds to discuss. All right, what do you think, Tanisha? What happens at 2 seconds? They have the same speed. Again, this intersection does not mean that they're passing each other like it did in the last graph. This is a different kind of graph. At that point in time, they have the same velocity. So make sure you're paying attention to the type of graph you have because you'll have that question for both types. And you need to make sure that you understand what that intersection point means. Okay. All right, at t equals 2 seconds, which hiker has traveled the farthest? So just as a reminder, I'm not going to ask anybody this one, although some of you hopefully know how to do this. Okay, but just as a reminder, on a velocity time graph, if I want to determine how far they have traveled, their displacement or their distance, I have to find area. Some of you asked me that on your assignment on Friday because you forgot from the first unit. Find the area. So at time of 2 seconds, I can determine each of their displacements by finding area because area is velocity times time. Okay, and that also is displacement. But when I find the area, for example, of the triangle that Art forms, it is his average velocity, which is 0.5 because he goes from 0 to 1. So halfway up, 0.5 times his time. Okay, which happens to correspond to the equation for the area of a triangle, 1/2 base times height. Okay, and so I would find his, and then I could find Polly's. This entire rectangle here is length times width, velocity times time. Again, that is displacement. And so looking at those areas, Art has traveled 1 meter, Polly has traveled 2 meters, and therefore who has traveled the farthest? Polly has, because Polly was moving the whole time and Art had to accelerate from rest to get to the same speed. So he's only traveled half as far because his average velocity is half as much. Okay, so again, find that area if you need to determine questions like this or find displacement. All right, here's the new stuff, because all that stuff was a review of stuff we've already talked about. Please copy down these 4 equations that are on my screen. Okay, in fact, you could even letter them like I did, A, B, C, D. But these are your 4 kinematic equations. The first one says VF equals VI plus A times T. In this equation, that is final velocity equals initial velocity plus acceleration times time. The second equation, which is letter B, is VF squared equals VI squared plus 2 times A times delta X. In that equation, that is final velocity squared equals initial velocity squared plus 2 times the acceleration times the displacement. The third equation, C, is delta X equals VIT plus 1/2 AT squared. In that equation, it is displacement equals initial velocity times time plus 1/2 times acceleration times time squared. In that equation, only the time is being squared. So just a heads up, it is just the T. It is not the 1/2 or the A. Equation D is displacement, or delta X, equals VI plus VF divided by 2. Please note that VI plus VF divided by 2 is the average velocity of whatever the object is, times time. Okay, so those are your 4 kinematic equations. We're going to try some practice problems using these equations. Because we have 4 different formulas to choose from, it is going to be super important when you read any question for you to start labeling the information that you have and the information that you're looking for so that you can choose the appropriate equation for that problem. As you move throughout physics, one of the hardest parts of this class is simply using the right equation. Once you know which equation to use, the actual math isn't very difficult. But if you use the wrong formula, you can't solve for the right answer. And that's not so much in this unit, although obviously there are 4 equations here, but as we move throughout the year, when you have more and more and more of them, it becomes more and more difficult and more important for you to label everything. Yes, ma'am?
What did you say AC stood for?
That's acceleration and time. All right, so we're going to start by labeling everything whenever we approach these. We're going to use something called the guess method. Maybe you've heard of it, maybe you haven't. We'll go over it. Okay, so this question says, a race car is traveling. By the way, if you didn't get the equations, they're still up here. A race car is traveling at 10 meters per second, exiting the pit. When it accelerates to 74 meters per second in 8 seconds, what is the car's acceleration? The G in my guess method, so the G on my screen stands for given, and we're going to label the information we have been given. For example, I'm given that the car is traveling 10 meters per second, so that's its initial velocity. It's going to then speed up to a new velocity, a final velocity of 74 meters per second. So we're just labeling what we know. That's going to be the G in our guess method. It stands for given. I know one other thing, and that is that this whole process takes a time of 8 seconds. Okay, so I have initial velocity, I have final velocity, and I have time. Again, when you label them, you also want to just glance really quickly at your units to make sure everything is consistent and that you don't need to do a conversion. And right now we're good because we have meters per second and our time is in seconds. That's awesome. Okay, my unknown is what U stands for in my guess method. So given, unknown, what am I solving for? What am I trying to find? And it's right here, what is the car's acceleration? So my unknown is acceleration. Obviously, if you want to solve for something, you need to pick an equation that has that variable in it. I can't solve for acceleration if it's not in my formula. Okay, the next step, E in my guess method, is to choose the appropriate equation. So looking at the information I have and what I need to find, I have VI, VF, T, and A. And if I look at these equations, A, B, C, and D, the only one that has all 4 of these things in it is equation A. Okay, so that's the one I'm going to use. For example, I couldn't use equation B because I don't know delta X, so I can't use it. I can't use equation C for the same reason. I don't know delta x, so I can't use it. Okay, equation D doesn't even have acceleration in it, so I wouldn't be able to use that because I can't solve for acceleration if it's not in the formula. So the only equation that allows me to solve this problem in one step is equation A. Now, could I solve for delta x first and then solve for A? You could. If you want to do twice as much work, you can absolutely do a two-step process. I would recommend just picking the one that you can do in one step most of the time. Okay, so this is my formula, VF equals VI plus A times T. The next step in my guess method is to substitute. Okay, so we're going to substitute into that equation. VF is 74, VI is 10, A is A, and T is 8. And so I get this, 74 equals 10 plus A times 8. And the last S is to solve. Okay, and so we substituted, now we're going to solve. I'm going to subtract 10 from both sides. That's going to give me 64 equals A, or 8 times A. And then to isolate this variable, we're going to divide both sides by 8, which gives us an acceleration of 8 meters per second squared. Okay, so pretty straightforward. I told you the math itself, I don't think you're going to find it to be super difficult, although you do have to remember just basic algebra rules whenever you're doing this. For example, when you look at this, you cannot add 10 plus 8a and call it 18a. Hopefully you already know that, but you can't do that. Those are not like terms. So you do have to remember those algebra rules and order of operations and all of that. But otherwise, it's pretty straightforward. All right, here are two more practice problems for you if you want to take a moment to look at them. It says, the first one says an object has an initial velocity of 4 meters per second. So I'm just going to label it VI. Okay, and a constant acceleration of 2 meters per second squared. I'm going to label that A. How far does the object travel in 20 seconds? How far is displacement? That's what I'm looking for. And I have a time over here. Okay, so again, with the information labeled, and you could write it on your paper and just actually write it out. I labeled it on the question. But I have VI, A, delta X, and T. So again, if you look at these equations, which one would be the most appropriate to use based on the information I have and what I am looking for? A, B, C, or D? Yeah, equation C, delta X equals VI times T, I have those, plus 1/2 times A, I have that, times T squared. Got it. I can solve for delta X without doing any rearranging at all by simply plugging into that equation. Okay, let's see. I'm going to put the answer up here, but I would like you to try it. You should get 480 meters. Okay, and then I want you to try the second one as well. I'm going to give you guys just maybe 90 seconds, a minute and a half to see if you can solve the first one and maybe even the second one, or at least get the second one set up, and then we'll talk about that a little bit more. So again, take 90 seconds. You can ask your neighbor if you get stuck, but try it on your own. Make sure that you feel comfortable using that equation. And then we'll come back and talk a little bit more. Okay, that may or may not have been enough time for you to do both. I don't know, but at the very least, hopefully you got the 480 whenever you plugged into that formula. If you didn't, we definitely need to figure out what you did wrong. But what about the second one? Okay, what equation did you choose to use for the second problem? Let's read it. A soccer ball rolls 110 meters, that's a displacement, to a stop. That's not a number, but that is information. That means it's not moving, so it's rolling to a final velocity of 0. You do need to be careful when you read these questions because you'll see things like this, comes to a stop, or you'll see things like starts from rest. And even though they're not listing the number in the question, that is information. They're giving you a velocity when you see those words. So just make sure that you identify that. So that's V up is 0. From a speed of 21 meters per second, that's my initial velocity. What is the ball's acceleration? A. So which equation should I use with this? Delta X, VF, VI, and A. Yeah, equation B. VF squared equals VI squared, I have both of those, plus 2 times A times delta X. Okay, that's the one you'd want to use if you want to do it in a single step. Now, could you use this information and solve for time first? Absolutely. You could use one of those other equations to solve for time, specifically D, and then you could use time to find A. But you could do it in one step instead if you just use equation B. Okay, and if you do that, your answer should be -2 meters per second squared. If you want to make a note of that on your paper, that's what you should get, and I would recommend that you try it. Make sure that you're getting that answer. Yes?
Wait, would VF be 0?
Yes.
Okay.
Okay, so try it, make sure you get that answer. I am gonna switch this slide though, so if you haven't copied the numbers down at the very least, go ahead and do that so that you can try it. And again, the answer you're looking for is -2.0 meters per second squared. By the way, this is slide 41 if you do want to open it back up to try it out later. Okay, but for the rest of the period, once you finish that one, or if you already feel comfortable with it, or if you're already done with it, you have the rest of the time in here to work on your assignment, which is 202.2 acceleration analysis problem set. You're going to find that problem set in the same Google Sheet that you were working in on Friday. So on Friday you did 202.1, or hopefully you did. Again, you're not actually submitting the sheet until we're done with all of the tabs. So although it said that it was due on Friday, I'm not actually checking it until Tuesday, okay, because that's when the whole sheet is due. But please don't save all of your work for Tuesday night, because you're going to be kicking yourself and be mad and say you had too much work to do, and I'm going to remind you that you had, you know, a week to do it. So again, over a week actually. So please start this now. You don't have to finish the whole thing today. In fact, we haven't covered everything yet that you're going to see on this assignment. So there's some stuff that you're going to see that you don't know how to do yet, specifically free fall, where it talks about things falling. We're going to talk about that tomorrow. But you should be able to do at least parts of it, or even most of it. I haven't counted how many free fall are in there. But that is what you're working on for the rest of the period. So go ahead and get your Google Sheet opened up. And if you have questions as you're working, please let me know.